Here's an interesting effect. If we start from Leedskalnin's PMH with two electromagnets arranged in opposite directions on a U-shaped bar of steel and put another little bar of iron or steel below with a wire coil on it, and we haven't connected the leads yet, and we put 30 volts into it DC and turn on the power, it won't jump until we get very close. Let's get very close to the U-shaped iron bar. Next, if we attach the leads from that third wire coil to the main power supply at 30 volts DC and turn on the power with a pulse, the iron bar will jump to the PMH even some distance away. That same distance when leads to the wire coil are not attached and we turn on the 30 volts, nothing happens. And when we attach leads from that third wire coil to the main power supply and turn it on again at 30 volts, it jumps from some distance away. Thus, in principle, this long distance jumping mechanism over 10 centimeters, maybe even over a foot, could be used to lift heavy rocks. If this was placed at the top of a tripod, this slightly below in the rock here, when you turn on the DC power as a pulse, the rock would go up 1 foot, you'd tighten the chain, you'd loosen it again, drop the crossbar, lift it another foot, loosen the chain, drop the crossbar, lift the rock another foot, and so on. Each DC pulse could lift the rock by, say, even 30-ton rock by increments of, say, 1 foot. Is that how Leedskalnin did it? Let's examine this hypothesis further. For the second half of this video, we're going to take another look at Leedskalnin's PMH. As you recall, we need a DC power supply, an on-off switch, a U-shaped piece of iron or steel, and on that we'll put two electromagnets in opposite directions and a square steel bar below them. Now when we flick on the power here, the square bar sticks and it won't fall off until we pull hard and then it falls off. So why is it sticking permanently? When we repeat this same experiment, but now with the electromagnets pointing in the same direction, north-south, north-south, and flick on the power, the iron bar sticks again, and then we turn off the power. Does it stay permanently bound? No, it just falls right off. Thus our hypothesis was that the flow of magnetic alignments around the bar, that way, and through the bar that way, is what's responsible for it sticking permanently. Do it again. It's stuck permanently until we break it. In order to test that hypothesis further, we can use an iron bar at the bottom with a third wire coil wrapped around it. Will that make it bind even stronger? First we're going to do the experiment where current's going just through that electromagnet and that one, but not through this one. You can see these leads aren't attached. When we turn on the power, we expect it to be like the previous case, just iron alone. Get closer, closer, then it snaps on. We turn it off, it's hard to take off. That's just like what we saw before where there was no third wire coil. Now let's add current to this coil and see what happens. Now we've wired it up so that these leads to this third coil go in parallel with these. So we all three coils, that one, create a clockwise circle around the iron bar. Now when we turn it on, now we get huge attraction from a distance. And we turn it off, it's still hard to break. So the distance at which this iron bar jumps to there is considerably larger than before. When we move the third wire coil even further away and turn it on, watch what happens. It still jumps about 2 or 3 inches. Without any current going through this iron bar, let's see how close we have to get. We'll turn it on. Get a little closer, a little closer. Keep getting closer and closer, closer. Finally, it jumps when we get really close. If we go up to 24 volts with current going through the coil, then it jumps over about 4 inches. So that's quite an impressive effect. The pull distance for this device seems proportional to how many amps I get coming out of my power supply. This particular power supply at 30 volts will go to about 10 amps. And when I turn it on, it'll go about 6 centimeters to close and pull. So I measured DC volts, DC amps, and the distance. And you see that particular power supply only goes to 10 amps, and I can only get it to pull about 6 centimeters. Here's another power supply, which is going to 15 volts and about 12 amps. And when I turn that on, you can see it's again about 6 centimeters. In order to get more power out of this, we have to use car batteries at 12 volts and lots more amps to create much stronger magnetic fields. And that's what Leedskalnin did, using banks of many car batteries lined up in a row. He could have put hundreds of amps into this thing.